interval 1 to 3. And it will need two boundary conditions. So we take one derivative boundary condition, du dx, at the left end, x equals 1 must be 2. And a Dirichlet boundary condition, u at 3 must be 1. Both inhomogeneous, as you see. Okay, so this has all the ingredients. It has a Dirichlet boundary condition, but not both, and it has a non-homogeneous boundary condition. And this is, of course, the strong formulation, BVP. Okay, now from this we can easily go to the weak formulation. So then by multiplying by an arbitrary test function and integrating, so integrate over the interval, the left-hand side, which is now simply the second derivative of u, times v, dx equals 0, and then we do integration by parts, to get 1, 3, du dx, dv dx, plus a boundary term, du dx times v, 1, 3 equals 0. And now we can apply the boundary conditions already. So 1, 3, this stays. And the boundary condition is applied here. Let's write it down first, and then I'll say what I've done. Minus 2v1 equals 0, since I've applied both boundary conditions here, that du dx at 1 equals 2, and that v, that's the boundary condition inherited from the problem here, and I've used v3 equals 0 by the rule of the weak formulation that the test function satisfies the homogeneous form of this Dirichlet boundary condition. Okay? So the weak formulation is, we've already proved that the strong implies this weak formulation. So weak formulation is that we need to solve this problem, du dx, dv dx, plus 2v1 equals 0, together with, we've already used the derivative boundary condition, so I don't need to copy that along. I can just write here u3, the Dirichlet boundary condition that we haven't used yet, and this then must hold for all v such that v3 equals 0. Okay, so that's the weak formulation. Have you already shown that strong implies this? Now we need to go back. Does this also imply that?